So in today's class, we are going to look into the connection between simple harmonic motion and circular motion. But before we start, let me give you some basics about the simple harmonic motion. So, in the last class, I have given you an example of a pendulum oscillating, or we can talk about a box which is connected to a spring and that is also oscillating. And those are good examples of simple harmonic motion. But mathematically, how do you define a simple harmonic motion? So let's go back to the situation. Maybe we have the platform and we, let's say, have a spring here, and this spring is actually connected with a box. Now, in case you are pulling the box in this direction, you basically have a force which is acting in the opposite direction, and that particular force is called the restoring force. So that means the box is set into motion. So that means there will be an acceleration. So this acceleration that we are talking about is directly proportional to the displacement. It's quite obvious because the more displacement you make for this particular box in this direction, and when you leave it, it's going to accelerate with a faster motion, right? So the motion is going to be faster, so the acceleration is going to be higher. So if the acceleration is directly proportional to the displacement, we can call it to be a simple harmonic in nature. Now, acceleration is force, mass, force is equal to mass into acceleration. So that means if acceleration is proportional to x, that means even the force should also be proportional to x. Now, these two conditions define what we call as simple harmonic motion. So in any case, in any situation, if you can prove that the acceleration is proportional to the displacement, we can say that the motion is more or less simple harmonic in nature. Having said that, let's try to connect simple harmonic motion and circular motion. So for this, let me imagine this circle, and let's say this is your center, okay? And we have, let's say, a ball at this end. Now, imagine you are having a plate and you are having a ball in it, and the ball is rotating in circles around this circumference. So this would more or less be your top view of that system. So what I'm having here is a ball which is rotating about a plate, and the same view or the same system can be observed from the side. So let's just have a look at the side view. So let me just draw this so that things becomes clear to you. So let's say this is your side view. So you can imagine the top view and the side view. For the side view, maybe we can actually take a straight line, okay, and when we observe it from the side, we can see it somewhere here, right? So what we can do now is you can think about this particular system, and let's say that the distance from here to the extreme end is a. So that would be the radius, which is actually also giving you the amplitude. So let me draw the figure and then the things will become more clear to you. So this particular position of the ball is, let's say, at time t is equal to 0. Now after some time, let's say, let me just take another time. Let's say t is equal to t dash, t is equal to t dash. The ball reaches here. And what you can do now is you can connect the ball with the center, and also let's drop a perpendicular here. So let's say the angle by which it gets displaced is theta, and we know this would be nothing but my angular displacement. And let's say this distance is more or less x. So what we are going to do now is we are going to look into it mathematically. So if we have a side view, what you can see is that the ball at this point, from the side view, we can observe the ball to be somewhere here. If the ball reaches at this point at t is equal to t dash, maybe we're observing the ball at this point. You have to imagine this or you can take a ball and put it on a plate and rotate it and check it from the top view and the side view. Now, before we proceed, let's do certain calculations. Now, if you look into this circular motion and we're looking into the top view, the angular displacement theta is written as omega into t. How? I hope you know your linear maths or linear physics. Velocity is equal to distance or displacement divided by time, right? So that means we can say the displacement is equal to velocity into time. Now, when we're talking about the circular motion, we can see that the displacement is in terms of angle. So in place of d, we can write down theta. This is velocity in linear motion, so we can talk about angular velocity omega into t. And that's how we are actually getting theta is equal to omega into t. So that we have. Now, if we just look into this entire picture, what you can see here is that this particular position also represents the amplitude. So this length is also the amplitude. So can we write down an equation for this? Yes. If we just do it from the top view, okay, let me just take the image, top view image. So from top view, what we can have is we can write down what is cos of theta, and let's see what is cos of theta here. So it will be nothing but b, that is the base, divided by the hypotenuse. So we can say this can be written as x divided by a, or merely the displacement can be written as x is equal to a cos of theta. But what is theta? Theta is omega t. So we can replace this, and therefore we can say that the equation for this motion is x is equal to a cos omega t. Now, if you can recall your earlier classes, you know that you have a cos function and you have an a, which is nothing but representing the amplitude. Omega is representing the angular velocity or angular frequency rather, and t is the time. So this entire equation has got a cos function in it. Now, if you have a cos function or a sine function, we know that the function will be more or less periodic in nature. So what do I mean by periodic? If I, plot a graph between time and displacement, we can see that the motion gets repeated after an interval of time. So if this is t1 and if this is, let's say, t2, or maybe I can write down this is t1 and this is t2, we know that it arrives at this situation after time t1 minus t2. So that means that will be the time period. So you can see that the motion gets repeated. Now such representation mathematically is possible if we can use a sine function or a cos function. So that means any periodic motion, when represented in terms of mathematical expression, we should be using a sine or a cos function. And that's how we usually write that the equation for a simple harmonic motion is having a cos function or maybe a sine function. So here we're saying that x is equal to a cos omega t is representing the motion. Now from this we can actually also find out what's the displacement. So what you can do now is let's do certain calculations and find out what's the displacement. Now you can also observe, if you look at from the side view, that if the ball comes at this particular position, I hope you can see the top of the screen, and if the ball comes at this particular position, in this particular case it will come exactly at the center. So this distance is basically the amplitude, right? This is the amplitude which you basically have to see from the side view. So please see, this is your side view, and from the side view this is the amplitude, and from the top view you can see the amplitude here, right? It's more or less the same thing. Now let's look into this expression further. Since we have the displacement, we can also find out what's the velocity. So let's calculate the velocity, and we have to use some simple calculus that you might have done in your lower classes. So velocity is written as v, which is nothing but the rate of change of displacement. So we can write it down as dx divided by dt. So that means it would be nothing but d dt of a cos omega t. Now if we do that, a is a constant, we can take it out. And when we take differentiation of cos function, we should have a minus sign, so I'll put a minus, and ddt of omega t would become omega, and then cos function will become sine function. So it is sine omega t. So try to recall this because these things will become more and more important, right? So let me just rearrange certain things here. I can simply write it down as minus omega a sine of omega t. And now I can also find out what's the acceleration. So the acceleration would be a can be written in a, and this would be nothing but the double differentiation of the displacement, or we can have it as the differentiation of the velocity. So I can write it down as dv divided by dt. So we have already found out also velocity, so I can simply write it down as d dt of minus omega a sine of omega t, right? T. So we have the minus sign, we can take it out. We have a, which is a constant, can be taken out, omega can be taken out, and then you take ddt of sine omega t. So you've got one more omega here, which comes out, which will be omega square, and sign differentiation is positive, so it will remain as positive, and it's cos omega t. But we have a minus sign from the velocity system. So now what we can do is, let me just rearrange this again. So I can write it down as minus omega square, and then I can write it down as a cos omega t. Now what you can see is that we have got a cos omega t, and what was our a cos omega t? It was nothing but x. So we can simply write it down as minus omega square x, right? So you see, omega for a particular system is more or less its frequency, which is constant, okay? So, or in this case, sorry, we can talk about it in terms of the angular velocity. So it's basically a constant. Omega is a constant because we are, moving from one point to the other at a constant angular velocity. So omega is a constant. So what you can say is the acceleration is proportional to the displacement. Okay. So if we say that, it means that it's a simple harmonic motion. So when we're talking about a simple circular motion, it is more or less simple harmonic motion, because by the definition of simple harmonic motion, which we actually discussed at the very beginning, is that the acceleration is proportional to x. And for any system, in this case, we have got a circular motion. If you can prove that the acceleration is proportional to the displacement, we can say that the motion is more or less simple harmonic in nature. So we can say that the motion is simple harmonic when we're talking about a circular motion. So that's it for today's class. But before we end, think about this, that we have a circular motion and we can see that this is actually rotating in circles. And when we're looking at it from the side view, we can see that this is actually having a to and fro motion from one end to the other. So basically, if you talk about the mean position, it will be somewhere here or here, which you will observe. And if you're talking about the extreme position, it will be either on this side or on this side. So when we look into it in a linear phase, you can see that the motion is going to be to and fro, right? So that's how you relate, a simple harmonic motion and circular motion. Until next class, take care.